Hello friends, I welcome you all in the lecture series of quantum calculations. In last lecture we saw how to install Quantum ESPRESSO on Google Colab and we run some basic calculation on Google Colab. As we move further, we will learn how to write a Python code to run a Quantum ESPRESSO file using atomic simulation environment. For that, we should have some knowledge about Quantum ESPRESSO input file. Today we will learn the input file of Quantum ESPRESSO. Okay. So this is the structure of a Quantum ESPRESSO input file. So here we have some segments which are shown in different color. So there are 5 to 6 segments. We need to learn about this segment one by one. Segments are start by this letter and we have name of the segment, and these segment are terminated by using this forward slash. Okay, so each segment is called as card. Okay, so there are a few cards available, and these cards are nothing but the input for the DFT calculation. We have control card, then after that we have system card, then after that we have electrons card, after that we have atomic species, atomic positions, and k points. Okay, so we will learn about this card one by one in detail. Now this first card is called control card. This card is specify the general control parameter for the calculation. Okay, next card is called system card. This card defines the physical and electronic properties of the your structure. Next we have electron card. This card control the electron optimization. After that we have atomic species. This define the atomic species which are available in your calculation. After that we have atomic position. This contain the for each atom what are the its position. Okay, and after that we have k points. So this k points define the grid for the Brilliant zone. Okay, so first we have control card. This card specify the general control parameter for the calculation. Now let's see which parameters are available under this control card. Okay, so first we have calculation. Okay, so this calculation define which type of calculation we are going to perform. For example, if we are performing SCF calculation, then we need to specify the SCF over here, right? Basically there are these calculation are available in Quantum ESPRESSO. We have SCF, non-self consistent calculation, we have relax calculation, we have VC relax calculation, we have MD molecular dynamics calculation, and after that we have bands calculation. As we move further, we will learn how to perform SCF, NSCF, VC relax and relax calculation. Okay, after calculation we have prefix. Okay, so this prefix is nothing but a unique name which is applied for the your calculation. Okay, for example, if I write example over here, then in your calculation folder, this example folder will contain all the files which will be generated during the calculation. Okay, for example, if you write a prefix as an example, so in calculation folder you have example.save folder. In that folder you have all the generated files and wave function in example.save folder. Okay, after prefix we have outdir. So outdir is a directory where you are going to save all your output generated files. If I write dot out over here, so during the calculation it generate out name folder. In that folder all the files will be generated. Okay, so pseudo directory contain the address of your pseudopotential. So you have to give the address or the folder address of your pseudopotential which you are going to use for the calculation. Okay, next is verbosity. So verbosity define the detail of your output. So there are basically two options are there, low and high in Quantum ESPRESSO. Okay, so next is T stress. So T stress is a parameter, is by default it is false, but when you are set it as true, it will calculate the stress tensor. This parameter is useful when you are calculating the strain or stress or bulk modulus. Okay, so this parameter is mainly used in VC relax calculation. After that we have T force. So by default it is always false, but when you are using it as in true condition, in that case it will calculate the force acting on each atom. Okay, so this calculation is useful when you are doing a relax or molecular dynamics calculation. Okay, so as we move further, we will learn how we can calculate the stress and force on the atom. Okay, next we have a system card. This system card define the physical and electronics properties of the system. Now let's see which are the parameter are used in system card. So first we have eyebrow. Eyebrow specify the crystal structure or Bravis lattice. Okay, so if I write eyebrow is equal to 1, in that case it is simple cubic. If I write 2 over here, in that case I am defining my system as a fence center cubic. For 3 it is body center cubic. For 0 it is custom lattice and it is defined by cell parameter. To visit the Quantum ESPRESSO input structure file, and here you can see all the file structure. Okay, I am not going into detail in eyebrow or cell DM because whenever you are defining this code in Python, the atomic simulation environment atom or bulk will have all these things inbuilt. Okay, so for the for the information purpose, I'm telling you what is cell DM. So cell DM is nothing but the cell parameter A. Okay, we all know that there are 3 cell parameter A, B, C, and we have 3 angles alpha, beta, and gamma. So cell DM1 is nothing but cell parameter A. Cell DM2 is nothing but it is a ratio of cell parameter B and A, and cell DM3 is nothing but cell parameter, it is ratio of cell parameter C by A. Okay, now next is NAT. So this number represent total number of atom in your unit cell. Okay, or how many atoms in your structure. Okay, so if we are using nickel oxide in a unit cell, in that case we have 1 nickel atom and 1 oxygen atom, so we have to specify 2 over here. Okay, next is n type. N type represent how many type of atom in your system. Again, if we are using nickel oxide, so we have nickel and oxygen, so in that case you have to specify n type is equal to 2. But if you are using silicon crystal, in that case you have only silicon atom, so you have to specify n type is equal to 1. So next we have E cutoff wave function. So this parameter is nothing but the cutoff energy for the plane wave in Rydberg. Okay, so this is 30 Rydberg. So we have to specify this value by using pseudopotential. In upcoming video I will show you how to choose this E cutoff value. Okay, next we have E cut rho. So E cut rho is nothing but charge density. Basically this charge density is up to 4 to 10 times or 4 to 8 times of the E cutoff energy. Okay, so next parameter is occupation. Basically that how the electrons are filled in your band. Okay, so by default it is fixed. So in insulating system we keep the occupation fixed, but for metallic or semiconductor we use smearing occupation. Okay, next parameter is smearing. So smearing is nothing but it is a method by which how your electrons are occupied near the Fermi level. Okay, so basically there are three techniques by which we are using smearing. First one is Gaussian, second is MP, and last one is tetrahedra. Okay, so next parameter is dgauss. So this parameter tells the how much broadening is used to occupation of electron near the Fermi level. Okay, so in this card, from this card we have to specify the E cutoff wave E cutoff wave function, E cutoff rho, occupation, smearing, and dgauss value when we are using atomic simulation environment. These value eyebrow, cell DM, NAT, and n time, all these parameters are taken by the atom environment or bulk environment in atomic simulation environment. Okay, next card is electron card. So this card control the electronic optimization. Okay, so let's see. So so next parameter is convergence threshold. This parameter tells that how much threshold is used for the SCF calculation to be converged. Okay, so for the large convergence threshold, the SCF calculation will take much time and it is computationally expensive. Okay, so next parameter is mixing beta. So this parameter is a factor which tell that how much uh, charge density is used from the previous calculation of self consistency field. Whenever we are performing SCF calculation, during that calculation the charge density is not directly calculated from scratch, but it takes some part from the previous calculation. Okay, and this parameter tells that how much factor is taking from the previous calculation. Okay, so as low as the mixing beta, the your calculation will converge towards the stability, but it will be computationally expensive. So uh, by default the mixing beta is 0.7, but during the calculation you can keep around 0.4, 0.3 or 0.5. Okay, so the next parameter is diagonalization. We have diagonalization, we have two methods. We have two options. First one is David and second one is CG, that is conjugate gradient. So basically diagonalization is an algorithm for solving the eigenvalue problem. Okay, next parameter is electron max steps. So this parameter tells how much iteration of self consistency calculation will be performed. If you are specifying 100 over here, in that case it will perform the 100 self consistency cycles. If you are writing 200, then in that case it will perform 200 SCF cycle. Next is we have atomic species. So okay, if you see carefully, after electron card we are not writing the card name using and symbol, and we are not terminating card by using forward slash. So after electron card we have to just specify the atomic species, atomic position and k points. Okay, so next we have atomic species. So this define the atomic species which are going to use in calculation and the pseudopotential file. Okay, so here we have written atomic species Si. So Si is a element silicon, its atomic weight and the file name of your pseudopotential. Okay, here you have to specify the file name of your pseudopotential. Next we have atomic position. So this specify the atomic positions of your silicon atom or any structure you are using. Okay, so atomic position, here have to, after position word you have to specify the by which type you are specifying the atomic position. Here if here it is written crystal, in that case a fractional coordinate will be used. If it is written Armstrong, in that case the Cartesian coordinates are used to specify the atomic position of each atom. Okay, here I have written Si, and this fractional coordinates of your first atom and second atom is specified. Next we have k points. So this define the k points which are used for the sampling of k grid in your calculation. Okay, so the k points define the grid size used for the sampling of your Brillouin zone. Okay, if here it is written 4 over here, it means we are using 4 grid in x direction, 4 in y and 4 in z direction for the sampling of your Brillouin zone. Okay, and after that we are writing the shift in the k points. So this is offset of grid. If it is written 0 0 0 over here, it means there is typically no shift in. Okay friends, so in this lecture we learn about the structure of Quantum ESPRESSO input file. The knowledge of Quantum ESPRESSO input file is necessary to write a Python code in atomic simulation environment. In next lecture I will show you how we can write a Python code to run a Quantum ESPRESSO file. Okay, thank you.